Okay, colleagues, welcome to this lecture on distributed systems, or better say distributed computing. I'd love to welcome you to this lecture. I'm your instructor, Mr. Chimanga Kashale. I'm going to be your instructor in this lecture on distributed systems. Before we could go any further in this lecture, what I'd love to actually assure you colleagues is that I'd love to encourage you to feel free. Okay, you have to feel free to participate in the lecture. Feel free to participate and feel free to ask questions and so on. I don't like a situation whereby it becomes more like a one-man show, or a teacher-centered kind of delivery. I don't like that. What I would urge you people is that you should feel free in the course of this lecture, so that we are able to build each other. We are going to understand how we are going to move together in this wonderful journey. Of course, with your background in data communication and networking, you find that looking at distributed computing will be such an amazing aspect, because you are just going to build on what you already know. Okay, so that is basically my preamble. Now, in the course of assessment, what we are going to do is we are going to have our continuous assessment out of 40, that is here, and this is going to be distributed as follows. The assignment will consist of 10 points, or rather 10 marks. Okay, and this is going to be given after a certain period when we start and so on. Then you're going to get to have your assignment, so that at least in your own time you are able to investigate and try to have a clear understanding of what is involved under distributed systems or distributed computing. Then we also are going to have what we call random quizzes. Okay, we're going to have random quizzes. When you talk about why do we say random quizzes, the reason is to allow you, or to encourage you colleagues to participate or to attend classes. Okay, so these random quizzes will be based on the topics of that particular day. Okay, will be based on the topic of that particular day, depending on what we are going to learn, and also what will necessitate this will also be the number of attendees. Okay, if most of you fail to attend classes and then you miss without any reason, then we may give a random quiz or random quizzes, and this may be out of, we may have two aspects, one and then the second one. Okay, then we also have what we call the labs. We could have the labs, which we are going to use some simulations, okay, to try and create some distributed systems, or systems that can operate in a distributed environment. This is another aspect that we are going to look at. Then in addition to that, we'll have a test which will also have 10 points or 10 marks. And then we are also going to have an exam to consist of 60 marks or 60 points. So basically, this is what we are going to look at. Okay, this is what we are going to look at. So all I would urge you people to do is feel free to participate, feel free to discuss, because we are going to have kind of open discussions. You could be put in groups. Okay, you could be put in groups, and in these groups you'll be allowed to, you'll be given certain topics in distributed systems where you'll be allowed to discuss and provide your different views, and then you'll be required to present as a group, where at least we are going to get the views of each and every one of us on a particular topic that we are going to get to discuss. Okay, so we are going to look at um, this course. We'll look at it in a unique way. Okay, in a unique way, whereby we are going to ensure that there's that group discussion, group participation, so that by the end of the day, nobody is left behind. Each and every one of us, at least, will be able to have an idea, or to be able to explain what distributed system is and how they can go about creating distributed system applications, and also how they can apply these concepts in real time. Okay, so with that said, I would like to now take you to what is expected of us. Okay, what we are going to learn in this uh, in this in this in this course. Okay. Okay, so let's look at the course content that we are going um, to cover in this lecture. Okay. Okay, that's the course content. Okay, so that's the course content. So we'll look at the first lecture will be on fundamentals. Okay, in these fundamentals, we are going to look at evolution of distributed computing systems. We are going to look at how the distributed system came into being. Okay, what is the basis or what is the genesis of distributed system? So we're going to look at this in quite detailed. Then, of course, like I said, with your background in data communication and networking, this is going to be pretty straightforward aspect to look at. Then, in addition, we'll look at system models. What are the models, particularly with the ones that are going to be tailored toward the distributed environment? Particularly, those are going to be tailored towards the distributed environment. That is going to be our main focus. Okay, then we also look at the issues in design of distributed systems. We're going to have issues to look at the issues. What are some of the issues that you as a computer engineer, okay, that you as a network engineer need to take into considerations as you design the distributed systems? Okay, what are the issues? Okay, what are the issues? So this is going to be something quite fascinating that we need to understand. Like I said again, your background in data communication and networking is going to play a critical aspect, a critical role in understanding these issues. Then also look at distributed computing environment. What is the environment that is associated with the distributed systems or distributed computing? Okay, all this will also be covered under fundamentals of distributed system. Then we also look at the web-based distributed model. Okay, the model. Remember, look at the system models. So one of the models to be considered is the web-based distributed model. Okay, so again, your background in web development, okay, will also play a critical role in understanding the web-based distributed model, which forms part of the distributed computing or distributed systems. Okay, then we also look at computer networks. Okay, computer networks related to distributed system and web-based protocols. Of course, we do have computer networks. Like I said, you have data communication and networking, where we learned about how the different types of networks, how you go about connecting devices together. Now, of course, that is a kind of environment which is maybe locally to an organization or within a particular town or within a particular country and so on. But what happens if we want to deal with information that is distributed across different countries using different networks and so on, or network types? How do you interconnect all those to ensure that there's a seamless transmission of information between these computer networks or between these systems and so on and so forth? So that is going to be a very critical aspect again that we are going to consider. Okay, so that is under the first unit. Then unit 2, we are going to look at message passing. Okay, message passing. Now, under message passing, we in a nutshell or in short, we are talking about passing information from one computer to the other. Now, these computers works, there are processes that works on those computers, and the aspect of message passing focuses on the computer, the processes being able to pass the message or communicate among themselves. One process located on one machine, or probably this process want to communicate or to pass a message to another process that is located in a different network. Okay, so how do they go about communicating? Okay, so that's where we'll talk about the aspect of inter-process communication. Okay, inter-process communication between one process and the other. Then also look at desirable features of good message passing. For you to be able to pass the message, okay, from one computer or from one process that is located on different computer, okay, we can say this is probably the let's say this is the PC1, okay, then we have PC2, okay. We can say maybe this PC is located on network 1, okay, or N1, and this one is maybe on network or N2, okay, and this may be distributed across countries, maybe, okay. Okay, these are distributed across the countries. Now, if this PC want to communicate to this PC here, so we are talking about having a process there. Okay, we have a process. Okay, process here, another process. Okay, so these two processes must communicate. This process which is located on PC2 and another process located on PC1 must be able to exchange information. Okay, must be able to exchange information as they communicate. So this is what we are talking about, inter-process communication. Okay, so this is inter-process communication. Okay, we'll look at this quite in detail. Then we are okay, I'll delete this. Okay, then in addition to that, we are going to talk about issues in IPC, okay, by message. Okay, issues. What are some of the issues that you encounter when you have one process, okay, one process trying to communicate to another process? What are some of the issues? Okay, particularly with a focus on message passing. Then there's an aspect of synchronization. How do they synchronize? We said we have we have network 1, okay, we have network 2, we probably have network 3. Now we may see that we have a process there we have a machine on network network 1, and now this machine has some processes communicating. Okay, then you have another machine here, or PC1. Also, this has a process, and then you have another PC there, and this one also has a process. Okay, so now what we are saying is that let's assume that this network is located in Tanzania. Okay, then this network is located in New Zealand, and then this one is located in Zambia. Okay, so now we have the pieces there. We have the PC on this machine, and on that one, maybe this one trying to, the PC here trying to communicate with the PC in this other network here. Now, it is basically the processes on that PC that are able to communicate. Okay, so now it's these processes that will have to exchange the messages. And now, considering the fact that these processes or these machines, or these machines are located on different networks, and this network is distributed across different countries. Now, how do they synchronize their communication? How do they synchronize their communication? Okay, so this is what we are going to look at. Then there's an aspect of buffering. Okay, how do they buffer the messages before communicating? Then we also look at the multi-datagram messages. What are these multi-datagram messages? We are going to look at them as well. Then you are going to look at the encoding and decoding of messages, of message data. Okay, then we'll have process addressing, then failure handling. Okay, how do we handle failure in such circumstances where we have networks that are distributed across different places and so forth? In such circumstances, how do we handle failure? Okay, how do we handle failure? Okay, so that's what we are saying. Now, then there's also group communication. Groups will talk about having processes, okay? Processes that are actually together, and they would want to communicate or send a message as a group. How do we go about doing that in the distributed environment? So this is very important, as this is going to be to help us in understanding the way communication takes place in a distributed environment. Then we'll look at the remote procedure calls, or what we call the RPC, remote procedure call. Now, under the RPC, or the remote procedure call, we'll look at the RPC model. Okay, when a machine, okay, which is in a remote area, okay, like the one we are talking about, one in Tanzania, another one in New Zealand, another one in Zambia, they want to communicate to each other. That's what we call the aspect of remote procedure calls. What are the procedures to start communicating with a machine that is distributed in a remote area? Okay, then you look at transparency of RPC, transparency of remote procedure call. Of course, when you look at transparency, it's not like the the way we understand the aspect of transparency, we will look at it in a different way, of course, to do with the way it is actually understood in the networking context. Then we'll look at how you go about implementing remote procedure call mechanism. How do you go about to implement the remote procedure call? Okay, then we look at the stub generations, okay, which are some of the procedures, some of the way you go about implementing remote procedure call. Okay, you look at implementing RPC. One technique is used, you use generate stubs. We'll understand what this is involved, what is involved in stub generation. Then also look at remote procedure call messages. What are the messages after stub generations? Then also look at marshalling arguments and result. How do you marshal the arguments and the result so that you are able to make that remote call to a different computer located, or to a different machine that is located on a different network, and this network is probably located in a remote country or remote network with different settings altogether. Then we also look at the server management. How do you manage a server? Okay, in the distributed environment. Okay, then you look at the communication protocols for remote procedure calls. When you talk about protocols, you're basically talking about the rules, just like we do have communication protocols that we use when you're communicating when machines are communicating with each other. So we have communication protocols that we can use when you are communicating remotely. Okay, when you are communicating remotely. So we also look at the complicated remote procedure call. Then we also look at the client-server binding. Okay, client-server binding. Before a client can send a message or can make a request to a server, there's some aspect of binding. Okay, they have to be binded before anything can be done. Then also look at what we call exceptional or exception handling. What happens if something wrong happens during the process of that procedure call? When you one machine is making a call, okay, trying to make a call to another machine that is in a remote location, suppose something fishy happens, what happens? So we'll look at the aspect of exception handling. Then what I say is some of the security issues. Okay, what some of the security issues that you must consider when you are looking at this remote procedure call. Then you also have what you call special types of RPCs. Okay, these will also be considered. Then, very important, we look at the lightweight remote procedure calls. Just like we do have lightweight processes and so on, we do have what we call lightweight remote procedure calls. We have this. And then how do you go about optimization, to do optimization for better performance? Okay, when you want to improve the performance. How do you go about that? So the optimization is basically needed for what we call distributed shared memory. Okay, so we'll look at the design and the implementation of implementation issues of distributed shared memory. Okay, sometimes it could be expensive to have a single process also having its own memory. That is why it is important that there's that aspect of shared memory, okay, which the processes can use in terms of what we call time sharing, time slicing, and so on. And this can work very well in an area where, in an environment where the memory scarcity is somehow handy. Then we also look at what we call granularity, also structure of shared memory space. Okay, so if the memory, is it every memory that is to be shared, or a shared memory should possess certain characteristics or certain structure, so that will also be looked at. Then also look at the consistency models. What are the consistency model? Okay, so this will also be looked at. Then replacement strategies will be looked at as well. Thrashing, okay, thrashing, and other approaches to distributed shared memory. And lastly, but not the least, you also look at the advantages of distributed shared memory. So this is about this will be our fourth topic on distributed shared memory. Okay, shared memory, very, very important. Okay, when you are dealing with distributed systems, okay, or distributed computing. Sometimes memory becomes a problem. Okay, you may not have enough or adequate memory. As a result, we are saying that it is very important that the aspect of share. Then there's also synchronization. This will be a unit. Okay, synchronization, we look at the clock synchronization. Of course, the clock on the processes, on the processors of the various machines, in order for them to be able to make an RPC, or for there to be some IPCs, or what we call inter-process communication, there must be some form of clock synchronization. Then event ordering. How do you go about ordering the event? Okay. Then we talk about the mutual exclusion. This is what we also we looked at in operating systems, particularly when we are looking at the deadlock conditions or situations. So we're talking about mutual as part of the synchronization of the processes. The election algorithms. These are algorithms that, okay, these algorithms that are used actually to make certain to choose certain processes for a particular activity. Okay, how do you settle to say, okay, this is the process that is going to handle this particular activity, and so forth. Certain elections have to be done. Okay, have to be done, and in this context, we are saying that the aspect of election algorithms comes in very handy in helping to synchronize the operations or processes that are taking place or taking part in what we're calling distributed system or distributed environment or distributed computing. Now, when you talk about memory, memory is a resource, process is a resource, and so on. So this takes us to Unit 6, which will focus on resource and process management. Okay, resource and process management. How do you manage the resources of in a distributed environment? Okay, so this is very important. So look at the desirable features of a good global scheduling algorithm. Okay, what are the features of a global, okay, scheduling algorithm? So this algorithm plays a critical role, okay, in identifying the computers that or the processes that are communicating over in a distributed environment. So this is going to be very, very important and very, very and then you also look at the task assignment approach, okay, which is part of resource and process management. One aspect of managing resource and process is what we are calling task assignment approach. It's one of the approaches where you assign tasks. Okay, then we have also what you call load balancing approach. Okay, you balance the load. Okay, you balance the load. Today we are talking about load shedding. Now it's part of load balancing, so that at least each one of us should have a bit of what is available. Okay, then we also have what we call the load sharing approach. Load sharing. Okay, this time you have power, but as you have power, it's not everyone that has power at that time. Okay, so you are sharing limited resources among the processes that are available. That you are calling resource management. Then you have process migration. You migrate a process. Then you have threads. You look at the threads that will allow you to do or to perform multitask using a single resource or similar resource. Then you have processor allocation. How do you go about allocate the processor to a particular resource or particular activity? Okay, then you have real-time distribution system. We'll look at this, but the key point to understand here is that as we discuss the resource and the process management, we are going to look at the desirable features of a good global scheduling algorithm, and now we have the techniques that are going to help us to understand how resource and process management is achieved. The first one is that of task assignment approach. Then we also have what we call load balancing approach. Then we have load sharing approach. Then we have process migration, then threads, then processor allocation, as well as what we are calling the real-time distributed systems. So this is basically, these are some of the activities or processes that will help us to mitigate the aspect of resource and process management. You use these techniques when you do not have adequate resources. Unit 6. Unit 7 focuses on files. Distributed file system. Distributed file system. So in this case, we are going to look at the desirable features of a good distributed file system. Okay? You could have a distributed system that is focused more on file sharing. Okay? On file sharing. The focus of a particular distributed system could be file sharing, just the sharing of files. Now we are saying, under this aspect, we look at the file models, the models of files, then file accessing models. How do you access the model? First, how do you share? Then how do you access the model, the files? Then how do you share the semantics? Okay, this is supposed to be sharing of semantics. Okay, like the techniques and so on used. How do you share them across in a distributed environment? Then you also look at what we are calling as file caching schemes. File caching schemes. How do you cache the files so that they are able to be accessed on a faster rate by other systems supposed to access the copy of a particular file type several times. You get it several times. Okay, once you replicate it several times, then it will be made available to other systems or other processes that may want to use that particular file. Then we also look at the fault tolerance in the aspect of distributed file system. How do we manage faults when they occur? Then also look at the design principles. Okay, look at the design principles, SANS network file systems. Then we also have what we call the Andrews file systems. And then you compare and contrast the NFS file as well as the AFS file. Okay, the network file system, SANS network file system, as well as the Andrews file system. So we need to compare these types of file system. Okay, we need to be able to compare this so that we understand in what circumstances should we use this and which one stands out to be better. The naming system. Okay, then to look at the desirable feature of good naming system. How do you name your system? How do you go about naming your system? Desirable features of a good naming system. Okay, so it's something that you need to understand. Then you have to understand the fundamentals, the fundamental technologies or terminologies and concepts with regards to the naming aspect. Then in addition to that, you look at the system-oriented names as one of the techniques for naming, what you are calling system-oriented. Then you have name caches. Then you have naming and security. Okay, naming and the security, and we have what we call the DCE directory services. Okay, so this is how what we are going to look at with regard to naming in the distributed system. Okay, with regard to naming in the distributed system. Then last but not the least, we'll look at what you are calling the case studies, what you call the match and chorus. You keep case studies as tutorials. We're going to have these case studies which we are going to keep as tutorials. These will be our case studies. Okay, so the teamwork and practicals. What we are saying is that each candidate will submit assignment based on the above syllabus, along with the flowchart and program listing will be submitted with the internal test papers. Of course, this will come to pass. But the key point we are trying to bring to your attention is that each one of you will be able to submit the assignment based on the above syllabus. Like I said, we are going to be put in groups. We'll be able to discuss the content. We'll be able to discuss. When you are put in groups, make sure that you discuss. We need to learn from each other. We need to be able to be open, and we need to be able to discuss. We need to be able to discuss the content and be able to understand really what is involved. So like I said, feel free. We need to be free. What are some of the reference materials or reference books that we could use? We could use the book on Distributed Operating System by Pradeep K. Sinha, PHI, or the one by Andrew Tenenbaum S. Distributed Operating System, Pearson Education. These are some of the books that you could use. There's also another book, very important, by Tenenbaum and Martin, okay, VS, Distributed System Principles and Paradigm, okay, Pearson Education, okay. Then you have George Colares, Jean Dollimore, Tim Koberg, and so on. So these also came up with a book called Distributed System Concept and Design. This is also quite a very good book which you can make use of, especially if you want to understand more the concept of distributed system. Okay, so this is what is required of us. Okay. Okay, so we are done with the content Okay, we're done with the content of okay, we're done with our content. Okay, so we're going to look at our lecture 1. Okay, colleagues, so we move on to our first unit, fundamentals of distributed system. Okay. Move on to the first. Okay. Fundamentals. Okay, in this the unit structure is as follows. We'll look at what is distributed computing system. What is a distributed computing system? The evolution of distributed computing system, and then we also look at distributed computing system models. Okay, so these are the three aspects that we are going to look at. Okay, what is a distributed computing system? Then the evolution of distributed computing system, then distributed computing system models. Okay, so this is what we are going to look at. So now, let's move now. What is distributed computing system? Okay. Okay, we need to understand something that over the past 2 decades, advancement in electronic technology have resulted in the availability of fast, inexpensive processors, and advancement in the communication technology have resulted in the availability of cost-effective and highly efficient computer networks. Okay, we are talking about the evolvement or the development in terms of technology. Okay, the advancement in microelectronics technology. Okay, micro, where we talk about the small aspect of integration, integrating different smaller aspect of devices together. Okay, so now this integration of different smaller electronic aspect has resulted in the fast and inexpensive processors. So we've come up with the processors that are able to process data at a very fast rate. But at the same time, these processors aren't that expensive as they used to be some years back. Okay. Now, again, in addition to having the fast and inexpensive processors, take note of this. Okay, fast and inexpensive processors. That's one thing. Okay, fast and inexpensive processors. Okay, then we have we are talking about the advancement in communication technology. Okay, so there are two advancements here. One, the advancement in microelectronic technology. Okay, advancement in microelectronic technology, which has resulted in fast and inexpensive processors. Two things: fast, okay, fast and um, inexpensive processors. Fast and inexpensive what? Processors. So there's advancement in what? In micro electronic technology. This has resulted in what? In fast and inexpensive processor. And then there's advancement in communication technology also. Okay, the advancement in communication technology, this has resulted in the availability of cost-effective and highly efficient computer networks. Very important. Okay. The advancement in microelectronic technology has resulted in fast and inexpensive processors. Okay, I'll highlight that. Whereas the advancement in communication technology has resulted in the availabilities of cost-effective and highly efficient computer network. Now we have computer networks that are not that expensive, but they are readily available such that they can be afforded by at least the majority of people across the world. Okay, so the net result of the advancement, okay, in these two technologies, which two technologies? Communication technology as well as microelectronic technology, is that, okay, what's the result? We are talking about the price. Okay, performance ratio has now changed to favor the use of interconnected. Okay, this has resulted in what you are calling the price performance ratio has now changed to favor what you are calling interconnected multiple processors in place of a single high-speed processor. Okay, so what are we saying? Because of these technologies, instead of us to be able to purchase one very expensive processor or one very expensive processor, what we are able to get is that at least you're able to get cost-effective processors. But now these are interconnected in a way that they are interconnected, but they are able to work together. Okay, they are able to work together. These are able to work together. Why are they able to work together? So that they are able to provide a seamless performance, very connected performance. Very important. Okay, so the two advancement. Don't forget that. Okay, now computer architectures consisting of interconnected multiple processors are basically of two types. Okay, so take note of this. Like I said, I'm not gonna rush. Okay, I'm not gonna rush. I'm going to take my time as I'm introducing this so that you are able to follow. Even in your own time, you are able to understand the concept, the way we are trying to connect the ideas here. Okay, we're trying to connect these ideas so that you don't really miss out the point. Okay, so we are saying, we did say that the interconnected the result of the advancement, the two advancement of this technology we talked about, has resulted in a price performance ratio that has now changed to favor the use of, which use is being favored, interconnection instead of a single fast processor. But we can have these processors now that are interconnected. Now, for you to come up with these interconnected computers or these interconnected processors or multiple processors in place of single processor, there are certain architecture that you need to understand, okay, for this aspect of interconnection. It's not every architecture that will allow you to have this interconnection. Okay, so what we are saying now is that computer architectures consisting of interconnected multiple processors are basically of two types. A computer architecture that consists of interconnected processors is of two types. So now again, colleagues, I'm going to highlight this. Now here we are talking about what? Computer architecture. Now, this computer architecture, we are saying this computer architecture consists of interconnected processor. It's not every architecture that has processors that are interconnected. Okay, but now these ones that are interconnected, this architecture, okay, are of two types. We have one which we are calling tightly coupled systems, as well as what we are calling loosely coupled system. These are the two computer architectures that we have. Okay, so now when you talk about tightly coupled system, we're saying in these systems, there is a single system-wide primary memory, okay, or address space that is shared by all the processors. Okay, so in a tightly coupled system, we have one primary memory. So we could draw something like this. We could say we have memory like that. Okay, now we have a lot of processors. Okay, we have processor 1, we have processor 2. Okay, then we could have processor 3. Now, all these are sharing this same, all these are sharing what? This same what? Processor. They are sharing this memory. Okay, we have, this is an example that we have. This is what we are calling tightly coupled system, a kind of computer architecture. We have, there's a single wide memory that is shared by all the processors. Now we are saying we have figure 1.1. We are going to see that. Okay. We're going to see that. So if any processor writes, okay, for example, the value of 100 to the memory location X, okay, what happens if any processor writes, for example, the value of 100 to the memory location X, any other processor subsequently reading from the location X will get the value 100. Okay? Because it is a shared memory. So meaning this will be available to everyone. So therefore, in this system, any communication between the processors usually takes place through the shared memory. So in these tightly coupled systems, shared memory. There is a shared memory. That's how you understand this. Okay? Now, let's look at the lost. We'll look at the diagram here. Now, let's look at the lost systems, the lost coupled systems. In this system, the processors do not share memory, and each processor has its own local memory. Okay, so in this case, you could find that each processor, okay, each processor will have its own memory. There's no central memory which is shared. Okay, this is loosely coupled. Now, just like we said, for that other, in that other aspect, if a processor writes the value 100 to the memory location X, this write operation will only change the contents of its local memory and will not affect the content of the other memories. Okay, the content of the other memories of other processors will not be affected, because this is what this is loosely coupled. Now, in these systems, all physical communication between the processors is done by passing messages across the networks that interconnect the processors. That is where now the secret is. Remember, we talked about in our preamble, we talked about message passing. So the communication now between the processors is through the message passing. Okay, so all physical communication between the processor is done by passing messages across the networks. So meaning the message has to be passed through the network. So these are the two types of computer architecture that consist of connected or having multiple processors. Okay, tightly coupled systems with a shared memory by all processors, and loosely coupled systems where each processor has its own memory. Okay, we have this is the first example A, where we said you have processor 1, CPU there, this one, CPU there, CPU there. So we have interconnected hardware. All these are sharing the same memory, of course, through a particular hardware. Okay, such that if this one processor write X in the memory, write 100 in a location called the X, then if this PC here or this processor want to access that location X, then it means the value that is going to be found there will be 100. Okay, so there's that shared memory. But in this case, unlike the tightly coupled, in the loose coupled, there's each processor has got its own local memory. Okay, but these communicate through what we are calling message passing, and the message is passed across the communication network. Okay, the message is passed across the communication network. So that's the difference between tightly coupled and loosely coupled multiprocessor systems. A tightly coupled multiprocessor system is A, and B, a loosely coupled system. So now, very important, tightly coupled systems are referred to as parallel processing. Okay? Tightly coupled is referred to as parallel processing, while loosely coupled systems are referred to these are referred to as distributed computing systems. Okay, so those where they're sharing the same memory, we are talking about um, parallel processing, because one processor can be processing a particular data, of course, using a certain memory location within the shared memory, and another one using a particular memory location. But where we have each processor having its own memory, this is what we are calling distributed computing, or simply put, distributed system. Okay, so in distributed system, we are talking about each processor having its own memory, its own memory, but the processors are able to communicate with each other through message passing. They're able to pass message across each other using the network infrastructure. Okay, they're able to use the network infrastructure. Now, in contrast to tightly coupled system, the processor of distributed computing system can be located far from each other to cover a wide geographic area. I'll highlight this. Okay. In contrast to the tightly coupled system, the processor of a distributed computing system can be located far from each other to cover a wide geographical area. Furthermore, in a tightly coupled system, okay, in a tightly coupled system, the number of processors that can be usefully deployed is usually small and limited. Okay, and limited by the bandwidth of the shared memory. Okay, so this is not the case with the distributed system that are more freely expandable and can have an almost unlimited number of processors. Okay, so here we are saying when you are looking at uncoupled memory, tightly coupled systems, you find that the number of processors that can be deployed can be small, okay, and limited because of the bandwidth of the memory. We're talking about the memory size, but now for the distributed aspect, there's no limit. Okay, there is no limit. You can have as many processors as possible. In short, a distributed computing system is basically a collection, okay, is basically a collection of processors interconnected by a communication network in which each processor has its own local memory and the other peripherals, and the communication between any two processors of the system takes place by message passing over the communication network. Now, colleagues, this is the definition of distributed system or distributed computing. Okay, I'm going to highlight this one. Okay, a distributed computing system is basically a collection of processors interconnected by a communication network in each communication network in which each processor has its own local memory and other peripherals, and the communication between any, okay, any of the two processors of the system take place by message passing over the communication network. Okay, so that's a distributed system. Okay, so for a particular processor, its own resources are local. Okay, for a particular processor, its own resources are local, whereas the other processors and their resources are remote. Okay, so together, a processor and its resources are usually referred to as a node or a site or machine of a distributed computing system. So oftentimes as we proceed in this course, we are going to see that we'll be making reference to a local machine as a node or a site or simply just a machine. Okay, so that is about the distributed system. Evolution. Okay, so this one, how did it evolve? Evolution of distributed computing. How did distributed computing come into being? Okay, computer systems are undergoing evolutions that we know. So from 1945, when the modern computer era began, until about 1985, computers were large and very expensive. Okay, they were large and very expensive. So even mini computers cost at least tens of thousands of dollars during that time. Okay, so you find that even mini computers at least costed quite some good amount. As a result, most organizations had only a handful of computers, and for lack of a way to connect them, these operated independently from one another. So operation of these computers in the olden days was independent, okay, because the computers were very expensive. So starting around the mid 1980s, however, two advances in technology began to change that situation in 1980. Okay, in 1980. So the first was the development of a powerful microprocessor. Okay, this the development of microprocessor changed the situation. So this was initially these were 8-bit machines, but soon we had the 16 32-bit machine as well as 64-bit CPUs became common from 1980s. Now, many of these are the computing power of a mainframe, which was large, okay, but for a fraction of the price. Now, the amount of improvement that has occurred in computing technology in the past half century is truly staggering and totally unprecedented in other industries. So from a machine that costed $10 million and executed one instruction per second, we have come to machine that cost about $1,000 and are able to execute 1 billion instructions per second, a price performance a price performance gain of about 10,013. Sorry, 1,013. Okay, so here basically what we are trying to talk about is the improvement in terms of the computing power, because in the olden days we used to have the computing power which was not so good, but the machines themselves were so expensive. But now we've seen a reduction in terms of the computing power, and the cost of the machine has also drastically reduced. Okay. Then the second development was the invention of high-speed computer network. Okay, so after the invention of the development of powerful microprocessors, after the processors were developed, then the network came into being. Okay, so the invention of high-speed computer networks. So the local area networks or LANs allow hundreds of machines within a building to be connected in such a way that a small amount of information can be transferred between machines in a few microseconds or so. So larger amount of data can be distributed, okay, can be distributed. Computing became popular with different difficulties of centralized became popular with the difficulties of centralized processing in mainframe. So after the aspect of centralizing became a challenge in mainframe, that is when the aspect of distributed computing came into being. So with the mainframe software architecture, all components are within a central host computer. Okay, all the components were within a central host. So users interact with the host through a terminal that captured keystrokes and send that information to the host. In the last decades, however, mainframe have found a new use as a servers in distributed client-server architecture. That's according to Eden in 1994. So the original PC, personal computer network, which have largely superseded mainframe, were based on file sharing architecture, where the server transfers files from a shared location to a desktop environment. Okay, they transfer this to a desktop environment, file transfer. Now, once that was done, um, the requested user job is then run, including logical data in the desktop environment. Okay, then under file sharing architecture. Okay, file sharing architectures work well if shared usage is low, update contention is low, and the volume of data to be transferred is low. Okay, so what we are saying is that we're giving you the history of how you need to appreciate where we are coming from to where we are now, and of course, for you to be able to appreciate the future. So I was saying the file sharing, which was the old technology, there was this um there was this update contention. Okay, volume of data that was being transferred was low, and so on. And in the 1900s or 1990s, PC LANs or personal local area networks, computing changed, became the capacity of the file sharing was strained as the number of online users grew and graphical user interfaces became popular. Okay, making mainframe and terminal display appear out of date. In 1990s, so the users of the computers grew, they became quite a lot. Okay, they became quite a lot now. So as a result, there was need for more and more improved way of sharing information across different networks. So the next major step in distributed computing came with the separation of software architecture into 2 or 3 tiers. Okay, so this was another major step in distributed computing, where um, the software also was separated. Okay, we talk about the 2 or 3 tiers. Okay, with the 2-tier client server architecture. Okay, 2-tier client server architecture, the graphical user interface is usually located in the user's desktop. Okay, it's usually located in the user's desktop environment, and the database management services are usually in a server that is more powerful machine that services many clients. So here we are talking about the client server paradigm, where we have the client. Okay, we have the client. So processing management is split between the user system interface environment and the database management server environment. So the two-tier client, locally distributed computing, when work groups are defined as a dozen to 100 people interacting on a local area network simultaneously. So what we are saying is that if you have at least, your network is to consist of at least 100 people who will be interacting simultaneously on a local area network, then you should consider to use a 2-tier client server architecture. Okay. However, when the number of users exceed 100, performance may begin to deteriorate, and the architecture is also difficult to scale. Okay, so meaning the two scale or the two tie may never be sufficient. Okay, so when the users increase above 100, then you may think of the three tie architecture, also referred to as the multi-tie architecture. This one emerged to overcome the limitation of the two-tie architecture. Okay, so in a three-tie architecture, a middle tier was added. Okay, there was a middle tier that was added between the user system interface client environment and the database management server environment. Okay, so what you need to understand is that from a start we had the one tier client server paradigm, one tier. Of course, this was only meant for few people or for few people communicating over the network. But as the number kept on increasing up to 100, you consider a two tier. Okay, but above 100, then you consider a three tier. But now, when you talk about a three tier, between the client and the server, what is there is what we are saying that there is a middle tier that sits to interface, to provide kind of interface between the client and the server. Okay. So there are a variety of ways of implementing this middle tier, such as transaction processing monitors. Okay, these are the ways of implementing the middle tier. Then there's also messaging middleware or application server. Okay, application server. So these are some of the ways to implement this. So the middle tier again can perform queuing, application execution, and database queries. Okay, so I'll label that. This is what a middle tier can do. Okay, can perform queuing of messages, it can execute application, and also perform some queries to the database. For example, if the middle tier provides queuing, then the client can deliver its request to the middle tier layer and disengages because the middle tier will access the data and return the answer to the client. So in addition, the middle tier add scheduling and prioritization for work in progress. Okay. So the three-tier client server architecture has been shown to improve performance for groups with a large number of users in terms of thousands and improve flexibility when compared to the two-tier approach. So expect a very high performance or improved performance. Okay, so I'm saying while the three-tier architecture proved successful at separating logical design of systems, the complexity of collaborating interfaces was still relatively difficult due to technical dependencies between interconnecting processes. Okay, so that is the issue. While we are saying, okay, this is much better compared to the two-tier, okay, the difficulty or the complexity of the interfaces, the middle tier we're talking about, was still a challenge. Okay, so because of that challenges, we are saying the standards for remote procedure calls were then used as an attempt to standardize interaction between the processes. Okay, So, meaning we are saying there was now the introduction of remote procedure calls. Okay, remote procedure calls to actually standardize. Okay, to basically standardize this complexity. Okay, the remote procedure call came into being. Okay, so as interface for software to use it is a set of rules for marshalling and unmarshalling parameters and results, a set of rules for encoding and decoding information transmitted between two processes. So a few primitive operations to invoke an individual call to return its results and to cancel it provides provisions in the operating systems and processes structure to maintain and reference state that is shared by participating processes. So RPCs requires a communication infrastructure to set up the path between the processes and provide a framework for naming. Okay, it provides also a process for naming and addressing. Okay, that's the remote procedure call. There are two models. There are two models that provide the framework for using the tools. Okay, when you're dealing with the remote procedure calls, there are two models. Okay, two models that provide the framework. Okay, so these are known as the computation model. Okay, we have the computational model and the interaction model. Okay, so the computational model describes how a program executes a procedure call when the procedure resides in a different process. Okay, so this one, the computation basically describes how a process execute a procedure call. Now, the interaction model, what does it do? Describes the activities that take place as the call progresses. Okay, one, okay, what does one does? The computation model describe how a program execute a procedure call. So it focuses on the execution of a procedure call, while the interaction model describe how the activities takes place as the call progresses. A marshalling component and an encoding component are brought together by an interface definition language. Okay, so the interface definition language brings together a marshalling component and an encoding component. So an interface definition language programs define the signature of a remote procedure call operations. So the signature is basically the name. Okay, the signature is basically the name of the operations, its input and output parameters, the result it returns, and the exceptions it may be asked to handle. Okay, that's the result. So RPC has a definite model of a flow control that passes from a calling process to a code process. So the calling process is suspended while the call is in progress and is resumed when the procedure terminates. So that's how the RPC works. Okay. it defines a model of flow of control. How does the flow of control move? The calling process is suspended while the call is in progress. Okay, so that process has to be suspended, and this calling process has to resume when the procedure terminates. Okay, it has to resume. So the procedure may itself call other procedures, and these can be located anywhere in the system participating in the application. Okay, this may be located anywhere in the system participating in the application. So we end here. Then we are going to find time. In our next meeting, we'll start from distributed computing system models. Distributed computing system model. So this is what we are going to look at in um, our next meeting. Okay. Thank you so much for your attention. We look forward to interacting with you, and we will see how we are going to proceed. Okay. Okay, colleagues, we end here. We end here and can call it as end of part 1 of lecture 1. So next time, in our next lecture, we are going to focus on distributed computing system models. Thank you so much for your time. Let's keep studying. Let's try to find time to go through. The reason why I developed this strategy is also to help you because of probably load shedding. At least you should be able to find time to go through in your own time. And if you fail to attend classes, at least you have time to go through and understand the materials that that has been discussed. Thank you so much, colleagues, and wishing you a blessed day and good morning.